The main purpose of this particular skill is twofold. The first is we need to be able to understand the interrelationship between the propagation speed, the wavelength, and the frequency. And these three parameters relate to each other directly, and you need to be able to move between the three. The second is to introduce the concept of transmission lines and be able to recognize when a transmission line consideration needs to kick in any given situation. So let's just start out by talking about what we mean by transmission line. So transmission line theory, and what the first part of this course is teaching you to do is to allow you to recognize the fact that a lot of the circuit theory that you learned so far, like Kirchhoff's voltage law, they have an underlying assumption. And that is, it can be stated several ways, but to me, what makes the most sense is to recognize that you assume that everything is instantaneously in a steady state during the time scales that you care about. Another way to view this is that if I transmit a signal down a wire, we assume the wire is short circuit, and that if I change the voltage in one end of the wire, the voltage at the other end of the wire changes instantaneously. And what that also means is that when I send in, say, a sinusoid, every part of that wire is all at the same phase at the same time. And when that is no longer the case, that means that you need to worry about what the situation is before everything's settled down. And that's when transmission line theory comes into play, and when you need to dust off the material that you're going to learn in the first part of this course. So let's just start out by looking at the basic relationship between propagation speed, wavelength, and frequency. So going all the way back to maybe potentially high school physics, we know that the propagation speed of a signal is directly the product of the frequency and the wavelength. And another way to look at this is in the case of the speed of light. In a vacuum, the propagation speed is 2.9979 2458 times 10 to the 8th. So it looks like a bunch of random numbers. The actual 8-string number is actually an integer. An interesting bit of trivia is that they changed the definition of a meter based on the speed of light in a vacuum so that it's actually a nice round number. Now, if it's not in a vacuum, it's going to be a little bit slower than the speed of light by some unitless quantity, which in optics we call n, or the refractive index. Another expression is we can also write that the speed of light is equal to 1 over the square root of the permittivity, mu, and the epsilon, and the permeability, mu. Now we can also break these into two quantities. We can say that in a vacuum, it's going to be the constant epsilon naught, and in a vacuum situation, the permeability is going to be what we're going to call mu naught. And similar to what we have, where in a vacuum the n here is equal to 1, and then if it turns out that you're not in a vacuum, the propagation speed slows down. We can also do the same thing here, where we can describe the material based on how its permittivity and permeability change relative to the situation in a vacuum. And so that constant adjustment is called epsilon r in the case of, or the relative permittivity, and mu r, which is the relative permeability. And so we can also rewrite this a different way to say that you have this quantity epsilon r and mu r, and 1 over the square root of epsilon naught mu naught. And so this, as we talked about before, this is the speed of light in a vacuum, and this quantity here is the refractive index. So another way to relate the refractive index, which is to the relative permittivity and permeability, is epsilon r and mu r. And then again, in your typical vacuum, traveling in a vacuum situation, these would all be equal to 1. But in anything else, it will be some number that's larger than 1. Now, Now so this relationship here, the propagation speed, which you can calculate here depending on if I give you some material parameters, you can calculate what this propagation speed is. And then with that, you should be able to relate the frequency to the wavelength. So if I gave you the frequency, then you should be able to calculate. If I gave you the wavelength, you should be able to calculate the frequency using that relationship, and then also you can solve for the wavelength if given the frequency. Now, one of the things that is important to keep in mind is also if you're sending in a sinusoid that has an associated phase, another really important piece of intuition is that if you capture a snapshot of a wave that's traveling in space, so it's traveling, it's going this way, you're capturing a snapshot, then the point between a particular phase, say the peak, and the next time you see it, that's the wavelength in terms of space. That is a total amount of phase shift of 2 pi occurs during that wavelength, right? So within a span of one wavelength, you're going to get 2 pi phase shift. And so the amount of phase shift over a distance d is when you calculate in units of wavelength, that actually tells you the amount of phase shift difference in terms of units of 2 pi that occurs during this time period. So using this knowledge, you can come up with a rule of thumb that we'll use later on in this class, which is you need to use transmission line theory when the critical dimension, so say the distance between a source or generator of a signal and the load on the other side, or whatever ends up being the largest wire length that you're worried about, if it's greater than 0.1 lambda. So in other words, if d is greater than 0.1 lambda, that means that if you say d is equal to 0.1 lambda, another way of saying that is that the amount of phase shift is going to be equal to 0.1 lambda over lambda times 2 pi, which means that if you're going from one side of the wire to another, you have a phase shift of, you have 0.1 of a cycle that has passed during the time period that between one end of the wire to another. Where, so say this is my generator, this is my load. If this distance here physically is greater than 0.1 lambda, that means that your generator and your load is going to be out of phase by 0.1 cycle, and in general that would be where we would have to utilize transmission line theory. Two other quantities to keep in mind. So just to summarize some quantities that we kind of introduced before. So again, c equals 1 over square root mu naught epsilon, which is the speed of light. So speed of light. And then another quantity that I'm just going to introduce here that we will be friends with later is you can also take the ratio between mu and epsilon. In the case of a vacuum, mu naught over epsilon. That will give you the characteristic impedance of the medium, which in the case of a vacuum is kind of is close to 376 ohm. So in summary, know this relationship here, how these interrelate, know the definition of the refractive index. And if I were to give you either a time scale or a length scale, you know how to correlate that between wavelength and frequency, and you should be able to use this rule of thumb to figure out whether you need to use transmission line theory or not.